Welcome to Calculus 3. We're going to dive into section 10.1. And one of the first things that I want to talk about is why do we need Calculus 3? Surely Calculus 1 and Calculus 2 was enough for anyone. Well, it turns out that so far in Calc 1 and 2, you studied functions of one variable, which we would often write, maybe we'd call the function f, and it's a function from r to r. So that's the notation that we would use. Maybe let's jot down an example. Maybe we would have f of x equals x squared. So then what? F of 2 would be 4. And if we wanted, we could actually graph this function of one variable. And when we graph it, we get a two-dimensional curve. And so I want to highlight that functions of one variable give us curves, two-dimensional curves. So curves in two space. All right, two space just means two dimensions. So one dimension, two dimension, there we go. All right, so in many situations, one variable just isn't enough. So maybe you want to talk about wind chill. Well, then you need to have temperature and wind speed. There's two variables involved if you want to compute wind chill. Volume of a gas, you need pressure and temperature of the gas. If you want to compute a batting average, you need the number of hits and the number of at-bats. And so all of these would actually be functions, it's kind of hard to read, functions of two variables. All right, so the other thing, going back to why do we need Calculus 3, we've made the case that oftentimes functions of one variable simply isn't enough. Going along with that, we live in what appears to be a geometrically three-dimensional world, and everything that you studied so far, functions of one variable, have a two-dimensional graph. And so we want to, at some point, talk about plots and surfaces and graphs in three space. And so when you're thinking about three space, then different questions come up. And instead of area, we might ask about surface area. How do you compute the surface area, maybe of a house or of a silo? You can ask about volume. What's the volume of your gas tank? Or you can ask about mass, the mass of a three-dimensional object. So we live in what appears to be a 3D world, and that raises lots of questions of its own that we'd like to be able to model. So in general, if you have a function of one variable, so this is your function of, and then if you have a function of one variable, you get a curve in, I'm going to write it as R2. That just means two dimensions. You get a curve in two dimension. If you have a function of two variables, you get what's called a surface in three dimensions. So I'll write it in R3. We'll talk about that notation in just a minute. So this is a three-dimensional surface. And if you have, in general, n variables, n here is arbitrary, bigger than or equal to 1. In variables, you get a quote surface, because it's not really a surface anymore. At least it's very hard to visualize. You get a quote surface in r to the n plus 1. So one more dimensions than the number of variables. And so this would be n plus 1 dimensional surface. Okay, so let's talk about this notation. So when I write R2, R3, what do I mean? Well, first off, R1 just means the real numbers, and you can visualize the real numbers as a number line. And so the number line is one-dimensional. You can go this way, or that way. There's one dimension to move in. So this is the real number line. When we write down R2, we mean the set of all ordered pairs A, B, such that both A and B are real numbers. And so, for example, the point 1, 2 would be in R2. That's in there because 1 is a real number, 2 is a real number. You can visualize R2 as just the two-dimensional plane that you're used to. We usually denote this axis with X and this one with Y. And so you can visualize R2 as all points in this plane. And I want to write down R3. R3 we're going to think of as the set of ordered triples A, B, C, such that A and B and C all live in the real numbers. So these are triples of real numbers. So for example, something in R3 at the point you could write down as 1, 0, negative 2. That would be a point in R3. How do you visualize the entire set? Well, you were going to add an axis. So we're going to think about this axis is the x-axis, this axis is the y-axis, and this axis is the z-axis. Basically, each time we go up, when we wanted to go from R to R2, we added a perpendicular axis, and we got R2. Now we're going to add another perpendicular axis, and we're going to go punch right through the plane, and that's the z-axis. So let's do just a quick example of plotting some points. So maybe we have the point 1, 2, 3. So 1 is telling you the x-coordinate, 2 is telling you the y-coordinate, and 3 is telling you the z-coordinate. So I'm going to go, this is the x-axis. When I draw the x, y, z coordinate axes, I'm going to always think about this axis is x, this is y, and this is z. And I'm going to orient it where this is this is positive x, and this is positive y, and that's positive z. So that's the perspective we're always going to take, just to make life easier. Of course, you're welcome to draw it differently. Just be sure that you label so that your readers know what you're talking about. So to plot this point, let's do it in pink. We'll go out 1 on the x-axis. We want to go out 1, 2 on the y-axis, and then up 3 on the z-axis. So somehow it's going to be up here somewhere. And it's helpful maybe if you plot some dots here. So we're going 1 on the x-axis out to 2 on the y-axis, and then maybe let's actually move it over just a little bit. It's going to be more right there. And when you drop that z-axis down, you're sitting over the point 1, 2. So here's the original point 1, 2 in the xy plane, and then you just go up 3 on the z-axis above that point. So really, if you can plot points in R2, then you do the same thing here, and then you just go above or below or on the xy plane, depending on whatever z is. So that's how it goes. So the last thing before we end this video, there's a question that pops up, and that question is, how do you know which way is up? When I put this z-axis through here, it's really quite arbitrary whether I make this the positive z's or the negative z's. And so the generally agreed upon method is the right-hand rule. So I'm going to show it to you on the screen, and then I'll show it to you visually as well. So on the screen, you put your right hand fingers, you start your fingers on the positive x-axis, so that's right here, and you let them point that way. So your fingertips are here pointing this way. Then if you're using your right hand, your thumb is always going to point up in the positive z direction. So let me show you that. I'm going to switch here to a different app. This is the Geogebra app. It's pretty cool, actually. If you have one of these, or if you have an iPad or an iPhone, you can get this. So there's my coordinate axes. The red is the positive x-axis. I can get my hand in here, hopefully. So I'm going to start my right hand fingers on the x-axis. They're curling towards the positive y-axis. You can see that's all perfect, and my thumb is sticking straight up in the positive z direction. So that's what the right-hand rule is saying. So let's switch back now to my writing app, and we'll end this video here.